So I mentioned a couple lectures back that you probably see where we're going with all of this, and of course now's the time to talk about the most common type of calculation involving mass and moles, and hopefully you're all ready for it, anticipating it, because you're going to see an awful lot of this. So here we are now, mass calculations for reactions. So now that we can determine molar mass based on a chemical formula, now that we can convert grams into moles pretty simply, what you'll often see us do here is take the moles of a given reactant or product, or the mass, and convert it to moles, and then move into moles of another reactant or product, and ultimately using molar mass to get the mass of that reactant or product that we're solving for. The most typical form of the equation set that we'll be working with involves mass of product from mass of reactant. So based on a number of grams of a given reactant, we can calculate the moles of that reactant using the molar mass. The molar mass can be given if I'm nice, or more typically you have to solve for it based on the formula. Right, I'm not going to do that every time because you only have a limited amount of time for the exam questions, but sometimes I'll be nice enough to give you the formula mass, but oftentimes you'll be solving for it. Once you have the grams of reactant converted into moles, you can use mole-mole factors to find the moles of product or other reactant, or we can start with the product and find reactant depending on how the problem's set up. Finally, once you have the moles of product in that most typical setup, then you can calculate the mass of the product based on the molar mass of that product. So this is a very common scheme. Moles of, well, actually, usually we start with mass of reactant A to moles of reactant A using the molar mass, then using mole-mole factors to go from moles of A to moles of B, and then finally using the molar mass of B to go to grams of B, where A and B are just any two species in a reaction. So get used to it, you're going to see an awful lot of it. Now let's work one of these questions together, and we'll see how we can take the mass of product from starting with the mass of a reactant here in this example. So acetylene gas, C2H2, burns in oxygen emitting high temperatures used for welding metals. How many grams of carbon dioxide can be produced when 54.6 grams of acetylene, C2H2, are burned? So we have our balanced chemical equation that tells us 2 moles of acetylene gas plus 5 moles of molecular oxygen gas in the presence of heat, some heat's necessary to get the reaction started, yields 4 moles of carbon dioxide gas plus 2 moles of water vapor. So our step 1 here is to state the given and needed quantities, and when we analyze this problem, we see that we're given 54.6 grams of acetylene. We need to know the grams of CO2 that can be produced from that, and our equation is given already balanced for you. Sometimes you'll have to balance it, sometimes it's already balanced. The other thing that I think is already bothering a few of you is we have to assume here that we have plenty of oxygen, because ultimately if we have limited oxygen, then we might not be able to react all of that 54.6 grams of acetylene. For this purpose, for this problem, let's assume we have plenty of oxygen around. Moving on to step 2, we need to write our plan to convert the given to the needed quantity. And here we're starting in grams and ending in grams, but as chemists, we're going to be making use of that mole, the chemist's amount. So we'll take our grams of acetylene to start. We'll use the molar mass of acetylene. It's not given to us here, but we're pretty much experts now at calculating molar masses from formulas. Then we'll be able to find the moles of C2H2 that 54.6 grams of C2H2 corresponds to. We'll use the mole-mole factor here from the balanced chemical equation to convert moles of acetylene into moles of carbon dioxide, and then finally use the molar mass of carbon dioxide to go from moles CO2 to grams of CO2, which is ultimately what we want. Now here in step 3, we'll use those coefficients to write the mole-mole factors, and we'll also determine those molar masses that we need. The molar mass of acetylene, there's 2 carbon atoms, or 2 moles of carbon atoms, and 2 moles of hydrogen atoms, and that gives us a total of 26.0 grams for 1 mole of C2H2. we have 1 mole of carbon atoms in carbon dioxide, 2 moles of oxygen atoms in carbon dioxide. When we sum those values up correctly, we should end up with a molar mass of 44.0 grams for 1 mole of carbon dioxide. The balanced chemical equation, now we see that for every 2 moles of acetylene gas that reacts, we produce 4 moles of carbon dioxide gas. So we know we're going to need those different conversion factors. It's just a matter of looking at the starting and ending quantities and figuring out how to set up that dimensional analysis strand so that we cancel the units that we need to cancel and we end in the unit that we need. So we need to start in grams of acetylene and end in grams of carbon dioxide for this example. Now we're ready to complete our problem here in step 4. We start with the 54.6 grams of acetylene. In order to convert into moles of acetylene, we need the form of that conversion factor where we have 1 mole of acetylene in the numerator and 26.0 grams of acetylene in the denominator. Now we've converted into moles of acetylene, and ultimately we need grams of CO2, but first we need to go through the mole-mole factor. 4 moles of CO2 over 2 moles of acetylene. The moles of acetylene now cancel. We're in moles of CO2. And then finally, to convert into mass of CO2, we need to multiply by 44.0 grams of CO2 over 1 mole CO2 to get a final mass of 185 grams for the mass of CO2 that could be produced when all of that acetylene is burned, assuming plenty of extra oxygen is present. So hopefully you're already catching on here. As I said, we're going to see this a lot, and we're going to see this again right now with another learning check. Now in this learning check, our challenge is to determine the mass in grams of ammonia that can form from 62.3 grams of nitrogen reacting according to the following reaction. And again, here we're going to have to assume that we have plenty of hydrogen gas, so we don't have to worry about running out of hydrogen. We're just going to stop once we've consumed all of that nitrogen. Using our familiar setup, we'll start with step 1 here, where we state the given and needed quantities. As we analyze this problem, we find that we're given 62.3 grams of nitrogen. We need to know the grams of ammonia that amount of nitrogen can produce, and we have our balanced chemical equation, right? It's done for us, fortunately. Be on the lookout, though, for unbalanced equations. Usually I'll highlight that in the text of the problem. I'll say according to the following unbalanced equation. So just be aware that might be another skill that I could assess in a problem like this. Moving on to step 2, we'll write our plan to convert the given to the needed quantities, either moles or grams. In this case, we're starting with grams and ending in grams, but obviously we'll need to use the mole as an intermediate value in order to make meaningful sense. We can't just look at grams and go to grams, or as you'll see, you'd end up quite wrong if you think that 62.3 grams of nitrogen is going to produce twice that gram mass of ammonia. That's not the case here. It's the mole that matters, and the mole is buried in this problem. We never talk about the mole. We talk about a mass of starting nitrogen. We talk about finding the mass of ending ammonia, but we never mention that we're going to have to go through the mole as an intermediary. So it's important in step 2 that you realize that, and that you take your grams of nitrogen, use the molar mass of nitrogen, dinitrogen, right, molecular nitrogen, to find the moles of nitrogen gas that 62.3 grams equals. Then we'll use our mole-mole factor to relate moles of N2 gas to moles of NH3 gas. And finally, we'll use the molar mass of ammonia to go from moles of NH3 to grams of NH3. Moving on here to step 3, we'll use our coefficients to write those mole-mole factors, and we'll, again, just like our last learning check, need to use molar mass values to start our reactant, the mass in grams, convert that into moles, and then finally convert the moles of product into mass of product. So looking at those molar mass values, 1 mole of N2 is equal to 28.0 grams of N2, right? It's N2, so we have to double that, 14.0 gram mass of a mole of nitrogen atoms. For the mole of ammonia, NH3, it's going to be 17.0 grams, right? 14.0 from that one nitrogen plus 3 times 1.0 from each of those hydrogens for a total of 17.0 grams for the ammonia. So that's our molar mass for the reactant and product of interest. We also need to relate those two. 1 mole of N2 gas yields 2 moles of NH3 gas according to the balanced chemical equation. So those are the values we need. Those are the possible ways we can set up those equalities as conversion factors. Our challenge is to move on to step 4 here and set them up correctly so that we start with grams of nitrogen gas, we end in grams of ammonia gas, and we've canceled all the units that we need along the way. All right, and here it is, step 4, where we actually set this problem up correctly and hopefully start and end with the quantities we are told. So we start with our 62.3 grams of nitrogen gas that was given in the problem. We convert that into moles of nitrogen gas by multiplying the conversion factor 1 mole N2 over 28.0 grams N2. Now we're in moles of nitrogen. We can now move into moles of ammonia by using the balanced chemical equation coefficients. So we see 2 moles of NH3 over 1 mole of N2. That will now move us out of moles of nitrogen and into moles of ammonia. Finally, since the question asks for grams of ammonia, we need to multiply those moles of NH3 by the form 17.0 grams NH3 over 1 mole NH3. Now moles of NH3 cancels, and we're left with a final value of 75.7 grams of ammonia. So clearly not a 1-to-2 mass ratio, but clearly a 1-to-2 mole ratio, and moles matter. So be careful. Just because I give you grams and want grams, don't get tricked. I've seen many students that think that they can use those coefficients as mass values. They don't relate masses. They only relate moles in a balanced chemical equation. Let's follow up with one more learning check here, make sure we're doing well on these topics. Okay, so in this learning check, we are asked how many grams of C2H2, that's acetylene, if you remember that from our sample problem at the start of this lecture, are burned if the reaction produces 75.0 grams of CO2. And we have our balanced chemical equation that should look familiar from earlier in this lecture. So a little different here, right? We're told something about the mass of product. CO2 is on the product side, and we're going to use that mass to figure out the grams of reactant, acetylene in this case, that were burned. It's also very similar because it's in a multiple choice setting to something you'll expect to see on the upcoming exam. So we have our answer choices here. You can see they're all sort of related, right? 88.6, 44.3, 22.2, they're roughly multiples of each other. So hopefully instead of just guessing, you're able to set this up and solve it correctly. So please go ahead and pause the video now, and when you're ready, we'll start back up and see if you selected the correct answer choice. All right, so like we do so many times, it should be second nature. Step 1, we state the given and needed quantities, and we analyze this problem. So we're given 75.0 grams of carbon dioxide produced. We need to know the grams of acetylene that burned to make that much carbon dioxide. And of course, we have our balanced chemical equation. Moving on to the next step, we have our plan to convert the given to the needed quantities. In this case, we're going to use moles and grams at different points. So we're going to start with grams of CO2 because that's what's given in the problem. We're going to use that formula CO2 to find the molar mass and ultimately then convert those grams into moles. Once we're in moles of CO2, we'll use the coefficients of the balanced chemical equation to figure out the moles of C2H2 that would have produced that much CO2. And finally, because our question asks for grams, we need to take the moles of C2H2 and convert it into grams of C2H2 by use of the molar mass of acetylene. All right, so here we are now moving into step 3. We're going to use those coefficients from this balanced chemical equation to write mole-mole factors. We'll also need to write molar mass factors for the acetylene and the carbon dioxide because we're starting in grams and ending in grams, so we'll need those as well. So 1 mole of CO2 equals 44.0 grams of CO2, right? Just using those values from the molar mass, and we actually did that, talked through it at least earlier on. 1 mole of C2H2 equals 26.0 grams of C2H2. And then we have to look at the balanced chemical equation to see that 4 moles of CO2 corresponds to 2 moles of C2H2. So now we have all those relationships. It's just a matter of moving on to the step 4 to figure out how to set this up correctly so that we start in grams of CO2, we end in grams of C2H2, and we've canceled all those intermediate units along the way. All right, so here we are moving on to step 4, setting up the problem to give the needed quantity, moles or grams. In this case, it's grams. So we start with that 75.0 grams of CO2. We multiply by its molar mass in the form 1 mole CO2 over 44.0 grams. So now we can cancel the grams of CO2 as a unit. We're in moles of CO2. And now that we're in moles of CO2, we can use those balanced chemical equation coefficients to see that we have 2 moles of C2H2 produced from every 4 moles of CO2. So we can cancel moles of CO2. We're now in moles of C2H2. In order to get finally into grams of C2H2, which is what the question asks, we need to multiply through by the form 26.0 grams C2H2 over 1 mole C2H2. That's going to allow us to cancel moles of C2H2 and to arrive at a final value of 22.2 grams C2H2, which was choice C. So it took a little while, but now you can check your work, see if you correctly answered it. Hopefully you correctly answered it because you did all the work correct, or if you just guessed C, well, you got lucky this time, but don't expect to get lucky again. So please do review these. There's lots of examples like this in the text, and certainly reach out to me if you're having trouble with it, because it's not going to go away. We do this all the time. Now that we have this grams to moles to moles to grams setup, you're going to see it again and again in the course. So please do reach out to me if you need help. If everything's going well, then we'll meet again here in the next part of Chapter 6 lecture.